Hello, I hope I'm audible.
Yes, to me.
Okay, so we'll start the meeting now because it's already 11:07. We cannot wait anymore. And thank you everyone for joining us today. And we will be continuing our series Astronova Sundays, which where we invite eminent speakers from across the world to share their knowledge and respective domain with us. We have Astronova is a club at University of Calcutta, and we are specializing in events offline and online like organizing lectures, skywatching, etc. It's based out of Institute of Radio Physics and Electronics, University of Calcutta. Now, as straight go to introducing our speaker for today, Dr. Souvik Bose. He is a research scientist based at Lockheed Martin Solar and Astrophysics Lab and NASA Ames Research Center in Palo Alto, California. He is also an affiliated researcher at the Roseland Center for Solar Physics, which is a center of excellence at the Institute of Theoretical Physics, University of Oslo. Dr. Bose did his BTech in EC followed by MTech in Astronomical Instrumentation and PhD from University of Oslo. His PhD thesis on the dynamics of specules and mass flow year was awarded as Best Thesis in 2022 by IAU. His research focused on using high-resolution observations and numerical models to understand the physical processes that cause the rapid rise of temperatures from 10,000 degrees to millions of degrees in the low solar atmosphere. He is a part of the IRIS satellite science investigation team and is also part of the upcoming NASA Multi-Slit Solar Explorer MUSE mission that is scheduled to be launched in June 2027. With this short introduction, I would like to thank Dr. Bose for accepting our invitation. And Dr. Bose, the stage is yours. Thank you.
Thank you, Arjun. I suppose you can see my screen and also the presentation mode, and also let me know if I'm audible.
Yes, you are.
All right. Yeah, thank you. So yeah, thank you so much for having me here, and it's really an honor. And also, I'm really delighted to be able to share some of my research aspects, like to students and also to the general public in general. Basically, the topic of my talk today is exploring the marvels of our nearest star, the Sun, and how it is like to live in close vicinity of such a star, which is so active and which has direct impacts on our space weather and so on. Without further ado, let's delve right in. But before starting the talk, I would like to briefly talk about myself, a little bit of a background. I'm from Alipurduar in West Bengal, in India, but I was born in Guwahati. And I did my BE in Electronics and Communication Engineering from University of Bardhaman in 2014. And then this was followed by the MTech in Astronomical Instrumentation from the Indian Institute of Astrophysics in Bangalore. And then I had a visiting researcher position in Germany, basically in Freiburg, at the Leibniz Institute for Solar and Physics in 2016. And immediately after that, I joined the PhD program at the Roseland Center for Solar Physics in University of Oslo in Norway. And I finished my PhD in 2021. And currently, I am basically working as a research scientist at Lockheed Martin Solar and Astrophysics Lab and NASA Ames Research Center from 2022 onwards. Anyway, so let's go into the more interesting aspects. So if you have questions about this, just let me know whenever. Feel free to interrupt. I generally want to keep this session as informal as possible, so just feel free to interrupt or raise your hand or just let me know if you have questions. I'm sure you might have many. So let me begin this talk by asking this question: why should we study the sun? Isn't this like a very constantly is a very constant star which rises and sets every day? Well, what I'm about to show you might change your perception a little bit. Now what you see here is the image of the sun, but in the extreme ultraviolet wavelengths. This is very counterintuitive to what you are probably used to seeing in broad daylight with the naked eye. You can see that it is so dynamics. I mean, overall, you see there are lots of. Yeah, by the way, this is Mercury, which is transiting in front of in front of the sun, and you see all these brilliant eruptions, also known as the coronal mass ejections. There are these bright structures which are the seats of some of the most energetic regions in the entire solar systems. And you see, these are what you call as flares. I'm sure many of you have heard about it, given that last week we had like a number of flares which led to very nice, well, substantial geomagnetic storms in the Earth's atmosphere, and also caused very nice auroras all the way. And you see all these dynamic events, these kind of flaring activities, these small scale jets. So it's I mean, so it's highly dynamic and hardly constant. So this is the same sun, basically, right? Which rises and sets every day, but we hardly are able to appreciate with our naked eye such unique and magnificent dynamics to some extent, if you want to say. So that's, I mean, and also the fact that we are so close to this kind of a star means that these kind of events like these flares and coronal mass ejections have a direct impact on our lives. Apart from the fact that you have, because the sunlight is very important for sustaining life on Earth. That's of course the foremost requirement for us. But in addition to that, there are direct impacts of these kind of highly energetic events, or that we actually see. Now, even then, you might still ask the question, why should you care? And that's right. I'm a solar physicist, so it's my job to care about the sun. But allow me to kind of give you a little bit of a perspective that why should the general public care about the sun? Now, I showed you this movie. This was a subset of the previous movie where you see this very nice eruption, which, by the way, it's called coronal mass ejections. And during this process, what happens is that there are, like, tons of particles like neutrons, and so on. They basically are hurled at high speeds, and if they're directed right towards the Earth, they can have impact on the Earth's atmosphere, as I already mentioned. And this video that is associated with that is also an example. It's of course an animation, and it's like a cartoon animation where you see that the coronal mass ejection, which was directed right at the Earth, causes an impact on the Earth's atmosphere and the Earth's magnetic field. So this is the Earth's magnetic field, if you can see my cursor. And because of the impact of the coronal mass ejections, the Earth's magnetic field tends to get reoriented, and it changes its configuration constantly. As long as the Earth's magnetic field is there, this is one of the invisible defense mechanisms that we have against these kind of eruptive phenomena that we or that basically occurs on the sun. And also because of these, we are able to see these wonderful auroras that we probably are, some of you are familiar with, like from last week. Now, from a very practical perspective, from a societal perspective, what can these kind of impact, what can these kind of eruptions have an impact on the society? Now, entirely, if, like, today we all know that our communication systems, our navigation systems, satellites, they're all in outer space. And when they're in outer space, they are not really shielded by this magnetic field, of the Earth, as you can see here, right? So whatever that's in space, they can be literally fried if conditions are not right. And if conditions are right, and if these mass ejections are directed straight towards the Earth, these electronic items or these electronic gadgets in space, including the astronaut health as well, the space shuttles, the satellites, can completely get fried. And also it can lead to substantial loss of satellite communication, GPS, navigation systems. And we know in today's world how important it is, this kind of technology is in our lives, because we cannot go these days from place A to place B without Google Maps. And if there is a significant impact, or if there is a very strong impact of these kind of events on the Earth, there will be no Google Maps. And there will be no internet, of course. So imagine the society, how backward will that be? So therefore, I think, mostly, at this point of time, maybe I'm able to convince you a little bit that why should you, the general public, care about the sun and what it is like to live near the sun. In my research, what I do is I compare, or well, I consider, or I basically look into the sun from a multitude of observatories, both from the ground as well as from the space. And there are reasons for this, which will be clearer as the talk progresses. But again, just feel free to interrupt me whenever if you have some questions. But these are the basically the suite of instruments that I use to look into the sun. We have observations from the ground-based Swedish 1 meter solar telescope, which has been functional from 2001. And this was the first telescope in the world to reach a spatial resolution of 70 kilometers on the surface of the sun, meaning that we can resolve features on the surface of the sun down to a scale of 70 kilometers, and that's huge. You can imagine the diameter of the sun is roughly 1.4 million kilometers. So in terms of that, if you consider that, and if you consider the resolution that we achieve, this is phenomenal. And this telescope still continues to function, and it provides high resolution observations of a certain region in the solar atmosphere, because you know that the Earth's atmosphere filters out certain radiation and the sun emits radiation in the entire electromagnetic spectrum. And fortunately, because of the Earth's atmosphere, like a very tiny portion of the entire electromagnetic spectrum is actually allowed. And this is good and bad in a way. Good because if we have the UV rays and if we have no filter, we will literally die from cancer. But bad in the sense that, to look into these kind of images that I showed you in the earlier slides, we have to go into space, because that's where most of the interesting things are happening on the sun. And that's the reason why I use data sets from these multiple space satellites. So one is, of course, the Solar Dynamics Observatory, which has been around for nearly 15 years now. And the images that you saw in these, in the past couple of slides, have been taken by this particular satellite. This is a phenomenal satellite. It images the full disk of the sun with every 12 seconds, and it has roughly, it sends down roughly 1.5 terabytes of data every day. Now, to give you a bit of a perspective, our average photograph that you take on a mobile phone ranges between 10 to 15 megabytes. So if you do the math, and if you compute, and if you compare the data rate of SDO or the Solar Dynamics Observatory, that would be equivalent of 150,000 photographs that you take on your smartphone. So we have this much amount of data of the whole disk of the sun from every day from this particular satellite, and it is still functioning. Of course, it's very old. There are degradation in the in the images, but it still works, and a lot of science, exciting science, is also coming up these days using this particular telescope. Then we have the Solar Orbiter, which is fairly new. It's actually the newest of the lot. It was launched by ESA, the European Space Agency, in 2020, and it is different from the other space satellites that I have shown here in the fact that, because this is a deep space mission, all the other three images that you see here, they orbit the Earth, and they are mostly in the low Earth orbits. But the ESA, the solar orbiter, it goes literally far off, and it can, and during the perihelion, it can reach a distance of roughly like half the distance of the sun and the Earth. So that's kind of pretty cool in a way. But because of that distance, it is not able to have such a high telemetry as, for example, a Solar Dynamics Observatory has. And then this is the oldest space satellite of the lot here. It's called the Hinode spacecraft, which was launched by JAXA, or the Japanese Space Exploration Agency, in 2006, and it's still functioning. It has a suite of 3 different telescopes. By the way, SDO has 3 different telescopes as well, which has not been detailed. But anyway, I'll skip that for now. And also the fact that this is IRIS, also known as the Interface Region Imaging Spectrograph, and I'm a scientist of the
Wait, wait.
IRIS mission. So this was launched. Sorry, is there a question? Anyway, okay. So yeah, so this was launched in 2013, and I'm a part of this science team as well, and it's still functioning. It's still kicking basically. In addition to all these observations, which are of course of very high quality, in order to truly understand what's going on in the sun, because you saw the sun is so dynamic, we also make use of a lot of simulations, or numerical simulations basically, or basically computer simulations. What you see here is basically the supercomputer here at NASA Ames. It's called the Pleiades, and it's one of the most powerful supercomputers on Earth. Well, it used to be the most powerful supercomputer on the Earth at some point of time, maybe like 15 or 10 years ago. But nowadays there are the Japanese supercomputers, which are of course much more powerful. Uh, but yeah, so basically what I wanted to say is I use observations as well as simulations and work in the synergy like of these two fields in order to understand the dynamics of the sun. Now, let's take a closer look. Now, this is the full disk image taken from the SDO. So it's one of the telescopes on the Solar Dynamics Observatory that looks into the photosphere, or what is called the surface of the sun. Now, if you follow me with this particular movie, we are zooming in into the surface of the sun, close to where these particular dark regions are formed. So this is an animation that is going down from the SDO, and now we have a very crystal clear, sharp image of these very fine structures on the sun from the SST. So this is the photosphere basically, and roughly the temperature of the photosphere, which is also termed as the surface, is about 5,000 to 6,000 Kelvin. And you see all these fine structures. Again, these fine structures are of course not visible if you don't have high resolution observations. And at the same point of time, you see that these particular structures, they resemble some sort of irregular rectangular patterns here roughly. And these are called granulation patterns. Now these granulation patterns are signatures of convection. So when nuclear fusion occurs in the core, which has roughly a temperature of 15 million Kelvin, of the order of 15 million Kelvin or so, the energy is transported via various processes like radiation and convection. So final third from the core until the surface, roughly about 30% of the distance, is where the energy is transported, or heat is transported in the form of convection. So imagine these particular structures that you see here, they represent structures which are akin to the structures or the features that you see when you boil hot water. So when you boil water, you see the bubbles coming out. And if you see a movie of this, which I'm going to show you, it is going to be like the bubbles which are coming out and going down. And that's the reason which you see here, that there are lanes basically between these two bright structures. And these are the lanes where the bubbles, or the gases, they come out from the convection zone, reaches the surface, and they basically cool off, and they eventually sink back down in the same way as you have like a boiling water. Now, the question is, what drives the interesting dynamics? We have seen that the photosphere, as well as the images that you have seen in the extreme ultraviolet, they are super dynamic. They are hardly stagnant. So what drives the interesting dynamics of the sun? The answer is the magnetic field. And we all know, we are all aware of the magnetic field from our textbooks in school, which looks like this. This is, by the way, a bar magnet, and I'm sure all of you know that. And these are the field lines that are associated with the bar magnet. But I wish the magnetic field on the sun would be as simple as that of a bar magnet. To really give you some idea about how the magnetic field changes, or how the magnetic field is actually playing a role in controlling all the dynamics, allow me to share this particular movie with you, where you see the extreme ultraviolet images on the sun, and you see here these are the magnetic fields at the surface. And here is the model, basically a kind of a modeling which connects these magnetic field lines, similar to the lines that you saw in a bar magnet. But again, you can see how complex these are, because it's not just one pole on the north and one pole at the south. There are multiple polarities everywhere, and all these polarities are constantly changing. They're reorienting in one way or the other. And see, again, we have this 171, or basically the extreme ultraviolet images. You see how dynamic it is, and also how the magnetic field is playing a role in actually controlling this particular dynamics. So we like, at least from this movie, it is very clear, it must be very clear to you, that magnetic field deeper down in the solar atmosphere must be playing some role. And again, I really would like to reiterate from this famous quote by Robert Leighton. I don't know if you have read the Feynman lectures on physics in your grad school or your undergrad. He was a co-author of the Feynman lectures on physics. Basically, it was Feynman, Leighton, and Sands. And he said that if it were not for its magnetic field, the sun would be as dull a star as most astronomers think it is. So and it's not just the case for the sun. We are able to see this or say this for the sun because it's so close, and we are able to resolve the details. But other stars, which are like the sun, and even which are older than the sun or newer than the sun, they have a very strong, component of the magnetic field, which which makes it very dynamic. It's just that it happens to be so far away from us that current telescopes are unable to kind of resolve the level of activity like compared to what we have for the sun. Now, an interesting question that you might have is, okay, I'm talking about the magnetic field, but how do we measure the magnetic field? It's not like we are going into the sun and we are actually measuring the magnetic field with an instrument, and I mean that's simply not possible. So what we do is we utilize something called the Zeeman effect, and I'm sure many of you who have had physics or who have had physics majors in their undergrad, they know what Zeeman effect is. But just to kind of reiterate, Zeeman effect is like an effect where you have a splitting of the spectral line. Now you see this is a case where you have the transition. So you have the 1s and 2p. These are different atomic the energy levels of an atom. And let's say that an electron is making a transition from the 1s to 2p. And then an association with this energy difference between these two levels, we all know from quantum mechanics that there is either a radiation absorbed or a radiation emitted that's proportional to the energy difference of these two levels. And this is actually causing, let's say, this kind of an absorption or an emission line here, right? Associated with this particular transition. Now, let's see, if you have magnetic field, like strong magnetic field associated, with this particular transition, what happens is that the electrons which are actually making this transition, they have their own spin, as we all know. It's called the spin angular momentum, right? To students who are who know this, and the spin of the electrons actually interact with the existing or the ambient magnetic field, causing it to have splitting of the upper energy level. And this is a very simplistic view of the Zeeman effect, of course, but this is why it happens. And as a result, now there are multiple transitions associated, associated with this particular atom, and it is causing basically three different spectral lines with slightly different energies because these energy levels are split. This is what Peter Zeeman discovered in 1896, and which eventually led him and his PhD supervisor, Henrik Anton Lorentz, to get the Nobel Prize, the second Nobel Prize in physics in 1902. Okay, all this is fine. But what do you do about the Zeeman effect on the sun? Assume you have this particular high resolution image of a sunspot. By the way, I didn't mention, and I guess many of you already know, these dark spots that we see in the photosphere, or the photo means light, right? Basically, it was named historically. So people saw, the photosphere is the visible layer that you can see with naked eye. So it was named as photosphere because it was the light's layer in a way. It's translated from Greek. And so these dark spots that basically appear, they are known as sunspots. And overall, these groups of sunspots are called active regions. So the sunspots or active regions are regions of strong magnetic fields on the sun. You have magnetic fields everywhere, right? If you remember the movie that I showed you a couple of slides ago, you have magnetic fields everywhere, but the strongest ones, the source and the sinks, are basically the ones where you have these dark spots. And why these spots appear dark? That is a question that you might all be interested to know. So on the sun, we have the plasma, right? You have the gas, basically the gas pressure, and also the magnetic pressure because you have the magnetic field. Now, in these regions, the magnetic field is so strong that the convection, right? The convection is inhibited. Magnetic field prevents convection altogether and doesn't let light or radiation pass through it, and that's why it appears darker here. So the darker the regions in the photosphere, the stronger the magnetic fields are. This is simply a very, like a brief overview of why sunspots look darker here. But anyway, what do we do with this? We have an image like this from the telescope or from a ground-based, like from a space-based or a ground-based data, and we take a slit. You know that when I was talking about the Zeeman effect here, and I was talking about a spectral line, and for spectral line, we need some sort of a spectrograph, right? Whether it's a filter graph, whether it's a grating-based spectrograph, whatever it is, we need the light to be split into its multiple constituents, right? Otherwise, we will not have this narrow line, as you all know. So let's imagine that there is a slit here, and which allows light to pass through this, and we let the light pass through this and get it diffract into a diffraction grating and so on, and we record a spectrum. So If we have adequate instruments, I'm not going into the details, this is what generally it would look like on your CCD when you have this particular spectral line, which is darker in color here, and this is along the slit. So you see that if you see, like if you follow the evolution in the y direction, you see that this region appears darker compared to here. And that's because the radiation here is lower, obviously, that you can see from here. And also note that these particular regions, they are split into multiple components, right? The splitting is not very obvious here. It depends upon the properties of the line. And by the way, this is the iron, the neutral iron line corresponding to this particular wavelength. And you know that from quantum mechanics, that the energy is equal to hc by lambda, right? So for the energy difference between these two layers or the levels, the upper level and the lower level, you have a corresponding frequency of the wavelength. And in this case, the iron, the neutral iron, because it's written one, this is a convention, it means it has a zero oxidation state. Two would mean single oxidation state. Three would mean double oxidation state, and so on. So this would be neutral iron, and the temperatures in the photosphere are more or less, it's about 5 to 6,000. So it's not enough to ionize iron. So therefore, you have neutral iron as well here, and this particular atomic transition corresponds to 630 nanometers. So roughly, if you would consider the Vibgyor, basically the rainbow part of the electromagnetic spectrum, this would correspond to close to the red or orange and red color. Anyway, but we don't have color CCDs, right? We have black and white CCDs most of the cases. But you see, like what I'm trying to say, these are two different lines of the same atom, and you see here in the region of the sunspot, it appears to be split into multiple components, similar to what you see here. But otherwise, the other regions below and above the sunspot, you don't see such splitting. So this is what we can infer straight away from the observations. And if you are careful enough with your measurements, if you have a CCD where you can measure the splitting as delta lambda b, which is basically the splitting between the delta lambda, let's say between the lowermost level here and the uppermost level here, then you can measure the magnetic field using this particular relationship, because this lambda naught is basically the center wavelength, which would correspond to 6302 nanometers. E naught is the charge of electron, 4 pi m is basically m is the mass of the electron, and c is the speed of light. So if you are careful enough in measuring the splitting of the spectral line, or the delta lambda that is associated with the transitions, the energy transitions between the uppermost and the lowermost level, you should be able to measure the magnetic field strength. This is what we basically utilize. And now if you repeat that for every, so if you now have the slits covering the whole field of view, let's say you have the slit here, you have the slit here, you have the slit here, at each particular slit position, you should be able to recover the magnetic field along the slit. And now if you can raster, this is what we call as the raster, where we basically use the slit to cover a certain part of field of view, you can obtain a 2D map of the magnetic field similar to this. So this is a different sunspot, but on top you see the photosphere in the same way, but in a colorized version, and on the bottom you see the magnetic field strength derived specifically from this particular relationship. Like the red indicates strongest magnetic field, green indicates relatively weaker, and from red to dark is from stronger to weakest magnetic field regimes. So you can clearly see from here that compared to the sunspots, rest of the region appears to be very weakly magnetized. Now, let me come back to the temperature structure of the sun. As you know, I'm interested in understanding the coronal heating problem, and let me try to explain what the coronal heating problem is. Now, you have seen this image. By the way, this image is from today. Well, here it's today. In your case, it's yesterday. So this is from 17th of May, as you can see, and this is UTC, so basically GMT today. And you see so many sunspots, and you know perhaps many of you that the sun is super active with so many sunspots and so many active regions. And this is what we know as the photosphere, right? And the photosphere, this is again in the iron, measured in the iron 1 line here, which is a different transition, so therefore a different wavelength, but close by you can see that it was 630 nanometers, it was 617, so pretty close, so similar temperatures. So this is roughly 5000 Kelvin. Now, this is what the magnetic field map looks like. And this is again from the SDO HMI from the Solar Dynamics Observatory. They have a technique, use Zeeman effect to measure the magnetic field. I'll blink the two just to show you that you have the magnetic field maps associated with this, and it's 1 to 1 more or less, and that's the photospheric magnetic field. Now, if you look at images that you see in the ultraviolet, and this is at roughly about 8,000 Kelvin, you start seeing these features which you don't see in the photosphere, right? You start seeing these intense bright features which you don't see in the photosphere. These features are known as plages. Basically, they have intermediate magnetic fields. They have magnetic field strengths between the sunspots and the quiet sun. So it's weaker than the sunspot, but it's quite strong compared to the quiet sun region. The quiet sun, by the way, is all the region on the sun that is not associated with strong magnetic field. That's what we call as the quiet sun. Though the quiet sun is still not quiet in a way, because if you look at the quiet sun as a whole, you would still be finding a lot of dynamics. But this is a comparison with respect to what we have on the active sun. So, I mean, you start to see emission, right? This is UV. So in UV, you start to see emission associated with this. But note that not everywhere you see this strong emission. So this is intensity. So you see this is strongly emitting compared to here, compared to these regions here. And this also surprisingly, well, probably not surprisingly, associated with the regions with strong magnetic fields. Again, magnetic fields is playing the role here as well, which we can see. Now, if you go further up, this is helium 2. This is the line observed in helium 2 at 300 angstroms, sampling roughly 90,000 degrees centigrades. You see that the dynamics and the morphology and the emission pattern completely changes. You see a lot more features, you see a lot more emission, and especially the emission is concentrated more in the regions where you have stronger magnetic fields. Again, this is also a way to say that the magnetic field is playing some role, right? Definitely it has to play a role. Otherwise, everywhere else, or this emission pattern would not be correlated with the magnetic field patches on a global scale. If you go even higher, let's say you go to about 800,000 Kelvin, well, this is roughly a million degrees centigrades. Look at now, you start to see features which are very unique to these particular structures, right? These, you see these loops, which you can see, these are basically the magnetic field loops, as you can probably guess, and they are rooted close to the active regions, because you saw that the magnetic fields in the sunspots, they can act because they're so strong. They act as, let's say the North Pole, and the other as the South Pole, kind of a configuration. And the other regions, you also see loops, but you don't see as prominently here. So, but the interesting thing is you see emission even at roughly 1 million Kelvin. Now, if you go even higher, so this is at 10 million Kelvin, as you can see, and look at the oxidation state of iron. Iron is oxidized. This is iron. This is iron 18. So it's Fe. It's Fe plus 17, if you would call it that way from a chemistry point of view. If you have the oxidation state, if you use the oxidation state nomenclature, this would be Fe plus 17, and this is at 94 angstroms, sampling 10 million Kelvin. And you see here that you see some regions like which are extremely hot, and especially the other regions which are not so strongly magnetic, you don't see much signal there, and it's obvious because the magnetic fields are not strong there, so the heating is not really strong enough to cause emission at roughly 10 million Kelvin. But look at this particular region, these active regions. These are images, like very current images here, so maybe like 12 hours ago. So this is super active, and this almost looks like it is a flare. So what I was trying to tell you here is that when you move from the photosphere, you have a regime where the temperature starts to increase as you go higher and higher up in the solar atmosphere. This is very counterintuitive. Imagine if you have a candle, right? If you have a candle as the heat source, now if you place your hand very close to the candle, you would feel obviously very hot. But if you slowly move away from the candle, the intensity of the heat would start to fall down. This is something that doesn't directly happen here. And that's why I have the temperature structure that I have shown here in the form of a graph here. It does happen to a region roughly about 500 kilometers from the center, right? Or from the surface in this case. So the temperature starts to come down, reaches a temperature minimum where it is roughly about about 5,000, about 4,500 Kelvin. But then as you move further higher and higher up, the temperature starts to go high. And these are the regions where you have the chromosphere, the transition region. By the way, the transition region is called the transition region because the temperature suddenly transitions from about 10,000 Kelvin to about about 100,000 Kelvin within a very small, about 500, within 500 kilometers in height. And then you reach the corona. So this is kind of counterintuitive, and this is called the coronal heating problem. And this is what my research specializes on. So, in a nutshell, this is what I'm trying to convey to you. You have the photosphere, which is roughly at about 6,000 Kelvin, and this is the source of magnetoconvective energy. And convective, so let me explain the term magnetoconvective. Convection, as you know, is basically where you see the granulation pattern, you see the heat transfer and the form of bubbles, granules, and so on. But here, because you have the magnetic field involved, it's called magnetoconvection. And this is the region where the source of magnetoconvective energy lies, definitely, right? And then you have the corona, where the temperature increases and it's roughly between 1 to 10 million Kelvin. But it's almost like, it's very hot, and we want to understand this problem. But interestingly, as you see, that heating the corona is not a big deal if you understand what's going on in between the two, in between the photosphere and the corona. Because roughly 1 to 10% of the mechanical energy that's produced in the photosphere is deposited actually in the corona, right? So it's something else that's going on in between, which we need to understand better in order to understand the coronal heating problem. We introduce a layer, as you saw probably in the previous temperature stratification, called the chromosphere, where it's roughly around 10,000 Kelvin. It's not super hot, it's just slightly hotter than the photosphere, but it's very dense. The corona is not dense at all. In terms of the density difference between the corona and the chromosphere, imagine if you have your desk basically that you use to study or keep your laptops, and if you basically have, you use water bottle and you pour water from a height onto the desk. The amount of density difference between the desk and the region above the desk is something similar to what you can experience here in the corona as you go from the corona to the chromosphere. So it's almost as if you're moving from air and you're hitting like iron, or like a piece of iron. So in terms of density, this is how dense the chromosphere is. But interestingly, most of the mechanical energy is deposited here. Heating the chromosphere to 10,000 Kelvin from 6,000 Kelvin is a harder problem to solve than to understand how the corona is heated to a million Kelvin or beyond that, because you don't have the density here. If you can understand this, you can understand this. And this is, of course, this is where you need multiple suites of instruments. You need to have multiple understanding of the different regions of the sun in order to understand it better. And in the chromosphere, if you look at the limb of the sun, basically from the edge, you see these jets, which are known as spicules. And they're basically the off-limb counterparts of these jets that you see here. This is where I'm looking straight into the sun, let's say the center of the sun, somewhere here. But if you would move your telescope from here to here, let's say on the pole somewhere in this region, if you can follow my cursor, this is where you see these jets shooting out rapidly. And this is where and these jets, they basically lie in the chromosphere corona interface. And because of this rapid shooting, as you can see, they keep on shooting up from the surface. It's thought that many of these jets, and they're ubiquitous on the sun, they're everywhere on the sun, many of these jets are responsible for transporting or depositing the magnetoconvective energy from the photosphere up into the corona. But it is not very simple to understand. So how does the heating takes place, right? Majorly, so this is, yeah, as I told you, I'll show you the movie of the granulation. This is what it is. If you see, this is again the photosphere. You see things coming up, going down, coming up, going down, and so on. And it's so dynamic. It's almost, and by the way, if you want to know, the size of one of these granules can be as big as the size of Texas or Madhya Pradesh or even Rajasthan. So you can imagine how big these granules are. And they're continuously moving up and down, up and down, up and down, and so on, right? And it is as I already told you, that this is where the source of the mechanical energy or the magnetoconvective energy lies. Now, how can this magnetic energy or magnetoconvective energy be deposited higher up in the solar atmosphere so as to heat the chromosphere and the corona? There are two possible mechanisms. One is the AC wave, the AC heating, also known as the wave heating aspects, which was first proposed by Hans Alfvén back in 1947. In fact, July 1947, before India got independence. And in this particular paper, by the way, Hans Alfvén got the Nobel Prize for a one-page paper explaining Alfvén waves in 1970s. It's amazing, the kind of mathematical simplicity that you have from Alfvén waves. But anyway, that's besides the point. So what the alpha? So how do you have heating associated with waves? So imagine if you have a guitar, right? You play. Many of you play guitar. Even if you don't, you know what a guitar is. And when you pluck the strings of the guitar, it causes the strings to be set into vibration. And this vibration is basically what the waves are. And when you have these waves propagate along the strings of the guitar, right? And it is through these particular waves and the dissipation or the damping of these waves is how we want to understand, or some people say, or in fact, Alfvén basically proposed this, that it's because of these waves which are taking place and like from the photosphere, and it is the damping of these waves, if you can understand them, that would lead us to understand how the outer corona is actually heated or how the outer atmosphere is heated. There is another theory proposed by Eugene Parker. Sorry, I should have written his name. But so if you know Parker Solar Telescope or Parker Solar Probe, basically that's it. It was named after him. So he proposed in the late 1980s and early 1990s that there is something called the braiding of the field lines, the magnetic field lines. If you remember the magnetic fields, imagine this is the magnetic field, one end of the magnetic field, and this is the other end of the magnetic field, and these are the magnetic field lines. Because of the motion that you see in the background, these magnetic fields can get tangled and twisted, and so on. This is called braiding. And many of you, and especially girls and women, they know braiding because in India, many women use braids in their hair. They braid and they make these kind of structures, right? And this is similar there. Because of this motion and the foot points, the magnetic fields tangle with each other. And because of this tangling, stress builds up. The magnetic fields are stressed, and magnetic fields don't like to be stressed. They want to release that stress. They want to release that tension. And during the process of releasing that tension, they can generate heat and they can generate kinetic energy. And this is a schematic of the same that basically tries to explain. So imagine that you have the opposite colors. They represent the oppositely directed field lines, and when they come close together, they reconfigure, and one of them they completely they get de-stressed. One of the component goes in this direction and the other component goes in this direction. So in both these directions, in the horizontal direction here, you would expect a large amount of kinetic energy as well as heat associated with that. So Eugene Parker proposed that because of this particular possibility, many events can actually be can actually heat the solar corona or even the solar chromosphere using this particular technique. So I mean, today, let me give you a disclaimer. We don't know for sure which particular mechanism works in explaining everything. We know that both of them works, but which one is the most dominant source, that's still an open question. I'll focus more a little bit on the DC heating model or the braiding model because we have very advanced numerical simulations that can explain this Parker's theory. So this is a numerical simulation, by the way. This is a computer-generated simulation. This has nothing to do with observations. But if you look at this, this looks very similar to the image that you see here. This is an actual observation from the Swedish Solar Telescope, right? So this is a numerical simulation computed using the Bifrost code, which is developed in Oslo. And this is the associated magnetic field structures with it. Now, because we have the numerical simulation, one advantage is that we know everything associated with the simulation. We know the magnetic fields, we know the velocity, we can know the temperature, we can know the heating and whatnot. Like it is simply a set of equations, also known as magnetohydrodynamic equations. It's in a way it's called, I mean, basically when you have the Maxwell's equations and Maxwell's equation, you couple that in a field, I mean, in a like in a conducting medium in presence of magnetic field, you have MHD or the magnetohydrodynamic equations. You solve them and then you obtain these kind of things. Now, Interestingly, when this was a paper from Mats Carlson and collaborators in 2016, but that's not important here. But see here that this is a 3D representation, a top view of this particular structure, and you are able to see the loops here, right? These loops, they resemble the loops that you saw in the extreme ultraviolet images, and this is the side view. So as if you're looking from this direction, and you see this is the same structure again. You see that there are loops associated with that, and again, these loops are rooted in the strongest magnetic polarities in the whole simulation patch. These are the two regions where the strongest magnetic polarities are. The dark regions represents, let's say, a north pole, and the white represents south pole. And the color contrast, basically, the whiter the polarity is, the stronger the polarity is, and so on, right? And these regions represents regions of weak magnetic fields. So not surprisingly, like we have in the observations, this particular simulation was able to reproduce the observed behavior to to a significantly good extent, and it's a pretty good job given that it's completely developed from a computer model. If you want to look at the magnetic fields, these are just the loops, right? These are not, this is the temperature, for example. You can also look at the magnetic fields. As I told you, because we have the simulation, we can do everything if you want. So we basically focus in this particular region. Of course, if you want to see the magnetic fields here, there will be magnetic fields there, but this is just for the visualization, just to correspond to these particular regions. We show the magnetic fields from the side and from the top. Now, if you superimpose this is the temperature. This is in log scale actually. So red represents million Kelvin and green represents about thousands of Kelvin. You see, and blue intermediate. You see that in regions where you have these loop-like structures, or these magnetic field lines, they also coincide with the regions of high temperature. Now, when they analyze the magnetic field lines in time, so from top to bottom diagonally, like from row wise, it's an evolution in time. You see that the magnetic fields, they change orientation. These are different colors, but they are just shown for the sake of brevity. You see that about 100 seconds, these magnetic fields, they cross each other. They cross each other like this, and they stay, and they evolve in a way which resembles Eugene Parker theory that was proposed. That was, I mean, Eugene Parker's cartoon that was proposed back in the late 1980s. And in this particular background, like in this green color, we basically show heating, right? And if you are, so it's associated with Joule heating. So we saw Joule heating associated with this, and basically from this we can say that the regions where we see the magnetic fields kind of crisscrossing each other, tangling each other, they're associated with regions of strong heating, not just the temperature rise. Now, enough of simulations, and let me get back to fantastic observations again. So the first observation of specially resolved magnetic field braiding was observed by the sounding rocket called HIC, or the High-Resolution Coronal Imager, back in 2012. It was the first flight of the HIC mission. So HIC observed this particular region. So this is the image taken from the Solar Dynamics Observatory, but HIC only focused on this particular region, this small region. So if you have, the higher the resolution actually you want, or higher the resolution you have, the lower the field of view, the smaller the field of view you can actually observe, right? Because you would need huge CCDs to actually record the full sun in high spatial resolution compared to what you have now. By the way, the SDO, the detector size is about 4K by 4K, so it is 4096 by 4096. But but that's at a resolution of about 700 kilometers on the surface, 750 kilometers on the surface of the sun. Now imagine if you want to extrapolate that to 70 kilometers, you would need like 40,000 by 40,000 pixels on the CCD, which doesn't exist. So that's why they trade that. We need to observe smaller regions on the sun. And this is the HIC image, basically, again, the same filter, and this shows the difference in the resolution. This is again AIA, the SDO, but what is interesting is that this particular movie actually shows these braiding. These are actually images. We don't have the magnetic fields from this, but if you look at the evolution, this is actually an enhanced version of this image on the left. You see that magnetic fields, if you consider these are magnetic field lines, they twist, they evolve, they crisscross each other, something similar to what I just showed you in the numerical simulation. And if you look at the intensity here, it is associated with an enhanced intensity, right? So this is the first direct observation of spatially resolved magnetic grating. Now, we can also extrapolate, so, but this was focused only in the corona. Recently, we also used, multiple instruments to actually focus on chromospheric and coronal heating together, or study the correlation between chromospheric and coronal heating through magnetic grating using NASA's IRIS satellite, which is shown here again, just so that you can recapitulate. Combining that with High-C Flight 2.1. So this was launched in 2018, and numerical simulations to understand that. But just before going into the actual study, I just want to show you what IRIS looks like. So this is the image that was taken of IRIS just before it was launched, and this is what it is from the, kind of an AutoCAD design. It's not exactly AutoCAD though, but I don't remember what design is that. But it shows you the actual optical, the telescope, the optics design here. So you have a 20 centimeter UV telescope, you have a guide telescope, and a spectrograph, right? And this was the first light images of IRIS that was observed in 2014. Well, not exactly the first light, but the first flare, or the CME, that IRIS observed in 2014. And this is a comparison of the full disk SDO image, and this is what IRIS looks like. So you have a dark structure, the horizontal line, which is going back and forth nervously, and this is where the slit of the spectrograph is actually scanning a particular region of the sun, right? So this is where, when the light passes through the slit, if you remember the previous example when I showed you the magnetic fields, when the light passes through the slit, it diffracts. It basically splits up into its multiple constituents. As you know, that light consists of multiple wavelengths, and once we are able to study those particular individual wavelengths, we can diagnose information about the gas temperature, the gas velocity, the magnetic field, the density, and so on. So that's why having spectroscopic capabilities is very important. And IRIS was the first satellite that achieved the highest spatial resolution of the chromosphere and the transition region from space. Now, back to the study. In this particular study, what we did, we combined IRIS and High-C of an active region. So this is a half and half image, as you can see here. This is from IRIS in the chromosphere, which is about 10,000 to 15,000 Kelvin. And this is with High-C, where you see the loops. This is about 1,000,000 Kelvin. And what we found is the regions that are associated with the foot point of the loops in this particular region, they show enhanced temperature in the chromosphere as well. Using numerical models, we basically found out, we have numerical models for this as well. And if you're a physics student, you should know the structures. These equations, basically, this is the curl of the magnetic field. Simply from Maxwell's equation, you know that this corresponds to J, or the current density. And this is the curl of the curl of B over the modulus of B, and that kind of helps us to visualize the regions where you have high currents, or basically regions of high heating. So we found here that braiding of the field lines causes this heating. Braiding of the foot points, close to the foot points of the field lines, they cause current sheets, which when dissipated leads to the heating that you see in the chromosphere and in the corona simultaneously. Now, the final aspect, or the last aspect of this, the alternate aspect of this, is the wave-based heating, where it's the theory by Alfvén, where you have these different, the strings in the guitar, and you pluck it, and it produces a sound, and then the wave dampens, and overall it dissipates. The dissipation, or the dampening of the wave, leads to heating. So there are the numerical modeling aspects of these is very well developed as well, but the models have significantly, they still need some refinements, like in today's community, because the temporal resolution that you need to understand waves is almost often at the limit of our current instrumentation capabilities. So nonetheless, I'll still try to give you some overview from the observations based on what kind of wave heating we can expect. So these are again the images of spicules, or these jets which shoot up from the limb of the sun. If you look at these enhanced images, you see that these spicules not just shoot up, they also dance in the field of view, right? Along the plane of the paper. So this dancing along the plane of the paper leads to transverse waves, which basically can cause heating of the solar atmosphere as well. So, these are called Alfvénic waves after Hans Alfvén. And again, I'm showing you this particular image, which is these jets. And from this particular telescope, this is from Hinode, by the way. So Hinode basically shows that there are a multitude of transverse alpine waves which exist in the chromosphere, which have been shown in these seminal papers in Science that was published in Science and Nature, basically about 15 years ago. And they have shown that there exist ubiquitous waves in the solar atmosphere that is capable of heating the upper atmospheres of the sun. Of course, this is again the chromosphere. We don't have the coronal observations here, right? Then with the advent of IRIS, this is from IRIS again, we were able to sample upper chromosphere, or in the transition region, basically the region which is even higher up compared to what Hinode could achieve. We also saw the torsional motions, basically the twist associated with this. This is actually the Doppler velocities. So the red is away from you and blue is towards you. You see the twist associated with these specules or with these jets, and these twisting motions, they're associated with heating to at least 80,000 Kelvin. And this was something really interesting to show that these alpine waves, they basically can cause heating signatures in the atmosphere up until about 100,000 Kelvin. Now, does this mean that we have solved the coronal heating problem? Well, there are a few points which I wanted to discuss. First of all, the challenge is to identify the dominant source of heating mechanism. Till today, we don't know exactly which mechanism plays the dominant role and where exactly, and it can often be the case that both waves and reconnection based models, they are playing an important role, but the challenge is to determine which is the more dominant one. We need higher resolution observations covering multiple heights, because you know that this is coupled all the way from the photosphere up into the corona, and that can be a very difficult task because different telescopes have different restrictions. They cannot observe the same target often, and you need to be lucky, and also you need to have instruments that can do this at very high resolution. The imaging instruments that you saw, they provide limited diagnostics because they are just images. You cannot derive spectroscopic properties, you cannot derive the temperature, you cannot derive the densities, you cannot derive the Doppler velocities associated with that. So we need spectroscopic observations of the corona, which are very limited, and high resolution spectroscopic observations are lacking. They don't exist. And all these telescopes, they're getting old, right? SDO is 15 years old, IRIS is more than 10 years old now, and it's limited to the transition region. And Hinode was launched nearly 20 years ago in 2006, but Hinode is just the photosphere. So we need something new to solve or to understand the coronal heating problem better. Now the future lies in actually observing as you know, the future lies in having multiple, the future lies basically in obtaining spectroscopic capabilities. But unlike Iris, which has single slit, and in this case, as you can see, the slit is nervously moving back and forth, trying to cover a particular field of view. We need to do something better than this, because single slit lasters, they basically are not able to keep up with the dynamical evolution, and imaging data alone is not enough to provide these kind of plasma diagnostics. So we have proposed a new instrument, and that's under development, and it's called the MUSE satellite, which is basically the multi-slit, which stands for the Multi-Slit Solar Explorer. And this is built upon the heritage of IRIS. And as you can see, let me just stop here a little bit. As you can see here, it has two different telescopes. It has like a context imager. Apart from the context imager, it has like one telescope for simply imaging capabilities, and the other telescope for spectrograph capabilities, right? And to give you a bit more detail, if you're interested, these are the electronic components. I'm not going into that, but the spectrograph telescope has an aperture of about 25 centimeters. It has three different channels completely in the corona, and it can achieve a resolution of 0.4 arc seconds. That would mean a resolution of about 250 kilometers in the corona, and that is like IRIS but for the corona. And that is a revolution, because none of the instruments till today have achieved this sort of a resolution in terms of spectroscopic capabilities, mind you. And then you have the context imager, which is again a separate telescope, as you can see here, and that has a 20 centimeter aperture, and it will provide imaging of context imaging of the solar atmosphere in the chromosphere upper transition region and in the corona, with roughly like a third of the resolution of SDO AIA. And this is what it would look like. These are, of course, we don't have the data yet because the telescope or the satellite is still under development actively, but we show you what it would look like. So this would be the images of the context imager, basically the field of view covering more than the active region. And these particular multiple slits, it has multiple, I mean, uses multiple slits in order to keep up the evolution. This would be the region where the spectrograph would be concentrated. And from spectroscopic perspective, we would have multiple, temperature diagnostics covering from the transition region to the flaring corona. And because we would have the spectroscopic capabilities, we would be able to, achieve velocity and, the turbulence as well associated, and the temperature as well associated with these highly dynamic features, which is going to be a revolution. And what is unique about Muse? Now, let me show you a very interesting movie. This is my final slide, I guess. So the Hinode ice is basically like iris, which has single slit, right? Now, if it is going to cover a certain field of view, which is a flare, let's say a flare is going on, it needs to raster like iris. It needs to go back and forth, and it takes time to build up the field of view. A new telescope is coming up, which is a future of the Hinode, but that's a Japanese mission. It's called the EUVST, or the Extreme Ultraviolet Solar Telescope. This is again also a single slit spectrograph, but as you can see, it covers the field of view. It rasters faster than the Hinode. So it is, and at a much higher resolution. So you can see it's less pixelated here compared to here, right? But compare what it is in terms of the real, in terms of the reality. This is of course a simulation, right? And this is how the flare evolves in real time. It is very dynamic. It can evolve in time scales of minutes, seconds even. And this is how it actually evolves, and this is what is captured by the existing instruments and the future UVST instrument. But what if we have Muse? Muse will have multiple slits, covering these particular, the whole field of view, as I just showed you, and it would also raster. Now look at this animation. This is what Muse would be able to do. Compare this with the the existing instrument and with UVST. It is much faster, and this is almost capturing the dynamics in real time. And this is the Doppler velocities. I mean, blue is again towards you, the plasma is towards you, and red is away from you. And these are all 35 slits into playing into action. And the resolution, of course, is much better than the current spacecrafts that we have. Right. So the question that I asked you, can we solve the coronal heating problem with Muse? Well, we need to wait and watch, because we have seen that since as we had more and more observations, higher and higher resolution observations, we face more complexities, more challenges, but we can certainly learn a lot more. And who knows, maybe we can have a crucial idea one day and help solve the coronal heating problem. That would be it. Thank you.
Hi. Thank you so much. Now we'll be opening up for questions. If anyone has any question, then they can turn on their mic or they can write in the chat box.
Maybe people are bored.
Sir, I have a question.
Yeah.
Sir, like how in the heating of the chromosphere, like how the elements are deciding the temperature?
Sorry, how?
In the heating of the chromosphere, how the elements are deciding the temperature?
Okay, so it's basically, very good question. So it is not just in the chromosphere, but also in the corona. Can you see my screen?
Yes, sir.
Can you see my screen? Yeah. Okay. So as you see, we have different elements there, because as I mentioned, for example, if I go back here, or no, maybe this is fine. Yeah. So as I told you here, that we have an instrument, a back-end instrument that is able to kind of study the spectral lines. And in this case, let's say you have a transition between a lower level and an upper level in a very simplified sense. And based on the atomic properties, we know that what that wavelength associated with that energy transition corresponds to. So iron 1 in this case corresponds to 6173, but see, like 6173 angstroms. But if you go let's say to helium 2, right? So you are increasing the oxidation state, and helium, as you know, is an inert gas. It's a very stable configuration. To make it oxidized, to make it kind of ionized, you need to put in a lot of energy. And from quantum mechanics and from atomic theory, we know exactly how much energy would it be needed in order to convert a neutral helium into a singly ionized helium, and what would be the associated temperatures of that. That's how we know that what element and what is the, depending upon the oxidation state or the ionization stages of these elements, we are able to know that what is roughly the formation or the temperature that are being sampled. And to continue this further, if you look here, for example, you see the iron has an oxidation state of 8, or it's written iron 9, but it is iron plus 8. So you have to remove 8 electrons from iron atom, right? And this corresponds to a certain amount of energy, which corresponds to a temperature of about 1,000,000 Kelvin. This is how we know the different elements, and the same with the chromosphere as well, because the chromosphere is mostly singly ionized. You have either magnesium 2 basically, or calcium 2, and so on, but you have the neutral hydrogen as well. From the atomic theory and from the radiation transfer equations, we know roughly the formation temperatures, but those are details. But I think this is clear that if you are able to look at the oxidation states, you're able to know how much energy is needed to ionize a particular element. So most astrophysicists call elements which are not hydrogen and helium as metals, right? Nitrogen is also considered as a metal, but that's not a metal, we all know. But just for our sake, we'll consider that based on the oxidation states, you're able to know, you can able to understand what is the temperature. I hope that's clear.
Yes, sir. Thank you, sir. And sir, like how is the color also changing? Is it due to
Ah,
also due to the oxidation states?
no, no, no. I mean, these are false color images.
Uh,
These are false color images.
Okay.
Just make them look pretty.
Okay. So we'll go to the next question in the chat. What are the key physical parameters and conditions that you need to input into these computational models slash simulations?
Okay, good question. Let me try to go back. I mean, I barely scraped, I mean, touched the simulation aspect, right? But anyway, what people generally do is we, depending upon what's the ultimate goal that you want to simulate. Simulating, we want to simulate the whole sun, sure, but that's something not really specific, right? So in this particular simulation, they had opposite polarity magnetic fields. What people do generally is that you have a box, you have a 3D box, an X, Y, and Z box, and the Z basically samples the height, right? The Z equals to 0 corresponds to the surface of the sun, roughly, in a way, and Z negative would correspond to the convection zone, that is below the surface of the sun, and higher up would correspond to higher heights, like the chromosphere, you reach the corona. So generally what people do, and as we all understand from the magnetic field evolution of the sun, that the sun's dynamo, from the observation, the sun has a dynamo which is playing a role in creating these magnetic fields or creating these sunspots. We cannot go so deep in the simulation box, of course, because of the limitations of the computation. So in this case, what people generally do is they have some opposite polarity magnetic field patches. They artificially embed them deeper in the convection zone. They allow the magnetic field to evolve based on the MHD equations, as I mentioned, and then let the magnetic fields play, do, and also the convection sets in, and let them do whatever they basically evolve. They want to evolve in a way where they kind of reach a state which is less like in the direction where the entropy is positive. So that's the original condition. I mean, I cannot remember the full question. If you can remember, if you can just read again once, I can probably converge. I'm
Yes, the
blabbering perhaps.
question was key physical parameters and conditions that you need to input into the model
Yes.
simulations.
So yeah. Okay. So the key physical parameters would be to you would need to know what you want to simulate. Number one. Secondly, the size of the box, the resolution in the vertical direction, the horizontal direction, and the magnetic field.
Okay. We have a hand raised from Shekhar Munshi. Do you want to ask some questions?
Hi, Souvik.
Hi.
I am very much trying to understanding, but since I am not a student of science, it's very much a matter of proud to um, be associated with you and hoping your, I mean, all out success. And that's all. No question. Thank you.
Okay. Thank you. Thank you so much.
Okay, so we'll move on to, we have few more questions in the chat box.
I mean, feel free to interact. I think that's far
Yeah,
more.
that will be much
That's far
better.
better. I mean, speak up if you want, please.
Yeah, so Sonia
I
asked
just
that,
put the questions in the in the chat box, so I forget. Yeah. So go on. Sorry.
yeah. So Sonia asked that it would also be interesting to know about the software or simulation platforms that you're commonly using for this purpose.
Simulation platforms. I mean, these simulations are mainly. Sorry. Yeah.
Shekhar,
Simulations
can you
are
please
mainly.
সুবিককে বলো একটু এবার কোশ্চেন অ্যান্সার চলছে তো আমি তো হাত দিয়ে ফেলেছি
Can you mute perhaps?
শেখর মুন্সি ওয়ান্টস টু
Maybe the
টক
moderator can mute.
Yeah.
বলেছি তো কথা বললাম ও শুনতে পাচ্ছি না তো
Can you mute?
স্পিকার
Can you mute, please? I don't understand who the moderator is.
I think yes, moderator is done. Sorry for that.
Yeah. Sorry.
Yes, so the question was the simulation platforms or software.
Yeah, sorry. Yeah, so the simulation platform, as in if you want to know the code, it's called Bifrost, and it's coded in. It was originally coded from the legacy is from Fortran, and then it's from C, and so on. That's the code base, and yeah, and that's it. I mean, this particular code is not yet publicly available, but if let's say if people are generally interested in collaborating with us, then we make these snapshots, the simulation snapshots, available to them if needed. But this is a decision that I don't personally make because I didn't develop the code.
We'll be sharing the slides though if you don't have any problem. Like
Sure,
just
I have no problems. I can give you a PDF of the
yeah,
slides
that
if
would
you
be
want.
great. Thank you.
Because probably the slides are too heavy. I'm not sure. I need to probably send using Dropbox or Google Drive, perhaps.
Yeah, I
Anyway,
think it will
we
be
can do
okay.
that.
Yeah.
We can do that. Yeah,
Okay.
sure.
We have one more question from Shashwat. He said that can you show a simple simulation model like a very basic model for this purpose? I want to understand the workflow of the model.
What model?
Uh, he has not stated that. Do you want to turn on your mic?
Yeah, hello, sir. So,
Yeah, hi.
I just want to, since I'm very new to solar astrophysics, like,
Okay.
so how do you get
No worries.
started with it? So,
Mhm.
like, what simulation models exactly you're referring to? So, I wanted to know how basically this model works. Like, how do you, like, the workflow of the model to do some analysis?
Okay, so like very good question and interesting question, and I'm glad that you're interested in this. So as I think there was a question in the box that what are the initial conditions and what parameters we need to consider. So you would need to consider that, right? You would need to have, so depending upon the complexities, depending upon what you want to simulate, we basically we try to simulate the atmosphere of the sun in as realistic fashion as possible. We at the moment, even today, with our computing infrastructure and with our knowledge of physics, we are still not 100% sure about the details that the sun actually has in reality. So we have a lot of approximations, but that's how science works, right? And what we do is we solve these I mean, these are basically set of equations. I mean, if you're interested, you can look or you can Google MHD equations. It's called magnetohydrodynamic equations. As I
Okay.
mentioned, there are Maxwell's equations, which
Mm.
are like so. If you have an electrical conductor immersed in a magnetic field, you would have basically, or in a or in a magnetic field dominated plasma, you would have conditions that would be suitable for MHD. And then Maxwell's equations, they basically, I assume you're familiar with Maxwell's equations at least. So the Maxwell's equations would basically be modified a little bit. That would include the terms such as momentum, the conservation of mass, conservation of energy, and so on. And solving all those equations simultaneously, in a way similar to the Navier-Stokes equation. If you know the Navier-Stokes equation, that would be what that is what the computer does. And normally those kind of solutions are not possible analytically. There are ways, there are solvers to actually account for these differences, these different equations, and they are solved in an iterative fashion. And given the initial magnetic field, given the initial conditions, the equation, we basically let it evolve, follow the equations, and then we have an atmosphere. An atmosphere in this sense would represent, like an atmosphere would represent basically a map of or a snapshot of temperature. We would have the density, we would have the magnetic field, we would have the line of sight or the total velocity, we would have pressure, and so on. And once we have that, we also want to compare with actual observations, right? Because observations are the key to understand whether our models are working or not working, whether we need refinements or not refinements, and so on, and where we need the refinements. So we do radiative transfer. We basically allow the radiation to interact with matter, we interact with the plasma, considering polarization like the Zeeman effect or not Zeeman effect, even just with the intensity, without considering the interaction of or the influence of magnetic field. We are able to synthesize, we are able to generate something called the synthetic observables that we want to mimic with what we want to see. And then we try to compare what we have and what we have in the observations and what we have in the simulations. And based on that, we try to refine our models. This is more or less the workflow. This is what the workflow is, more or less like that, right? And we have some knowledge from the past, from the 70s and from the 60s, when supercomputing was not really that advanced, when people basically relied on 1D, basically one dimensional modelings, and they're assuming hydrostatic equilibrium, assuming different approximations. So today we are doing much better, but we are still, I think, quite far away from simulating the whole sun accurately.
Okay.
Thank you, sir.
If anyone else has any question, they can ask it now. Um, Please turn on your mic, Shmonjit.
Yeah, hi, Dr. Souvik. First of all, thank you for a very elaborate and very nice presentation. It was really insightful, and I have a question. Like you are talking about the coronal heating problem, the temperature structure. You showed those slides. So I just wanted you to comment on the relation between these things that you have shown, this temperature profile and all, and its relation to the acceleration of the solar wind and like the type of different types of solar winds, like the HSS, like the high speed streams, or the slow winds. How are they related? If you can briefly just can highlight, that will be wonderful.
Okay.
Thank you.
Right. Thank you, Shumanjit, for the question. Yeah. So I did not really focus on that solar wind and the solar the aspects of the solar wind, of course. But in this particular case, I would say that again, the magnetic fields, they play a role in also channeling the solar, like the solar winds, as you know. In this particular, well, today I don't think I have like an image that shows a coronal hole. But anyway, solar winds, people think, or at least the fast solar wind in this case, people think they originate from coronal holes. And coronal holes are regions of open magnetic structures. Okay, but you can say magnetic field, the divergence of magnetic field is always zero. How can you have open magnetic structures? Well, they're locally open magnetic structures, and we think that they extend, the magnetic field lines, they extend over the entire heliosphere, and they reconnect somewhere back in the sun, because like Gauss's law has to be obeyed, right? And again, there, because this opening, the open structures there, the magnetic fields, the magnetic field lines are open, and as a result, the plasma, which is frozen with respect to the magnetic field, they allow the propagation of the solar wind along those magnetic field lines. And those solar wind, they interact with the outer atmospheres of other planets, if they have magnetic field, and so on, and that leads to some other effects. Now, the temperature structure that I'm talking about, these, I mean, overall active regions, or the what I'm trying to convey here is that they are kind of related, but also not directly related problems, because the coronal heating problem specifically looks into the temperature changes as you move from the surface to to the higher temperatures. And the solar wind, which is again a question, that what is the origin of the solar wind, because there is still no compelling evidence of what actually leads to the solar wind there. So that is again an open question, but that is a different problem, which is of course in a way related, because magnetic field plays an important role. uh, so I guess you're getting the point. I mean, if you have like follow-up questions, you can ask, and that will be easier for me as well. But what I wanted to convey, or finally, is that the origin of the solar wind and the origin of the coronal heating problem, they are commonly linked in a way, because both are driven by the magnetic fields. And I mean, everywhere magnetic field is playing a role, but they're slightly different problems. I mean, so far the data and the understanding that we have, we understand that there are two different problems. Understanding the solar wind would not necessarily lead me to understanding the coronal heating problem, and vice versa. I hope I could make
Yeah. Thank you.
you
Yeah.
know.
Thanks a lot.
We have one more question. Except for the high resolution and the large memory required, are there any other challenges you encounter in achieving a high fidelity representation of the solar flare phenomena?
Oh, absolutely. I mean, it's not just the computer limitations. We need observations, right? We need observations of the magnetic field of the corona. What I showed you here, in no, not this one. This one? No, not here. So I just want to play this movie again. So I mean, at some point in this particular movie, you see these lines, right? These blue and red lines. These are magnetic fields, and yeah, specifically these ones. These are from models. These are not real magnetic field observations. And on a global scale, at the scale of the full sun, I mean, it does a decent job. But you know how dynamic these kind of events are, and how important the need for high resolution observations are after what I presented today. So we need coronal magnetic field observations. Even chromospheric magnetic field observations are hard to obtain, because you know what happens. The magnetic field lines, let's say if there are field lines, because field lines are, they're an imaginary concept, but let's say there are field lines. So the magnetic field, they open up, they diverge, right? They kind of spread out as they move from the source and higher up. So the effect of the magnetic field is kind of diluted in a way. So the Zeeman effect, let's say if you're using Zeeman effect to measure, the magnetic field becomes weaker, and therefore the Zeeman effect is not as strong, and therefore you cannot measure the magnetic field. I'm talking about this in the chromosphere. So today we don't even have like synoptic or long-term measurements of the chromospheric magnetic field with high degree of accuracy. Forget about the corona. Aditya L1, which was recently launched, I guess would want to do that at some point of time with the VELC, where they would measure the coronal magnetic field. But we are still awaiting results on that. So unless and until we have that crucial ingredient, apart from whatever numerical resolution, and also the infrastructure in terms of computing, I think we have significant lacking in terms of the physics itself.
Okay. If anyone has any more questions. Okay, I think they have asked their questions. So we'll be closing our session now. I'd like to thank Dr. Bose for this wonderful session with the great explanations and the animations as well. Um, and we'll be sharing this recording. We have recorded this entire session for those who could not attend it, and we'll be uploading it on our YouTube, and we'll be sending it as a mail as well. And as Dr. Bose said that he'll be sending his PDFs as well, so we'll be attaching that with the mail too. Thank you very much for joining us, everyone, and thank you so much, Dr. Bose, for your wonderful talk.
Yeah, you're welcome, and thank you so much for having me. And just one comment in the slides, in the basically in the main the intro first slide, I'll put my email address as well, in case if you are anyone has questions, they can always email me and I can get back to them.
Yep. Thank you so much for that.
Thank you.